Okay, I'd like to invite Lucy on stage. Lucy's come all the way, again, part of the Curtin team, so thanks Lucy for coming. She's going to talk to us about impacts of space.
Thank you very much for having me. I've only been here today, but this has been an awesome event, so congratulations to everybody who's been involved with this. So today I would like to talk to you about impacts in space. Now I want to start by saying I haven't specifically worked on Murchison. I'm currently trying to. It's proving a little bit challenging, but I would like to demonstrate to you hopefully today why impacts in space are relevant to Murchison and what perhaps we can learn from it. So when I talk about impacts in space, where have these impacts been happening? We've been hearing, we've just heard from Ellie, my colleague, about how we have meteorites that we find in the outback all over the world, and they have, I suppose, impacted onto the Earth, although maybe they haven't been quite as catastrophic as we think impacts should be. Now, we don't necessarily see these giant impacts as they're happening, but we do have evidence of those impacts in the form of impact craters. Now, we see those all over our solar system. So over on the left-hand side, we've of course got the moon. We can look up at the moon some nights and see these beautiful impact craters that have been forming for a long time. We can look at Mars, we can look at Mercury, and we can also look a little bit closer to home. So we can see evidence of these large impacts on Earth. Although on Earth, things are a little bit different because we have plate tectonics, which we've already heard about, and that's actually probably wiped out some of the impact craters that formed a very, very long time ago. So we know that these impacts have been happening in our solar system for quite a while. Now, the reason for that is, for a start, why would impacts only be happening now? They definitely were happening throughout the history of our solar system. So on the left-hand side, this is just a plot of, this is to do with the moon. So we have a number of craters, and those craters relate to impacts on the moon. And then we can use that to work out the age of the surface of the moon. And my manager, actually, Gretchen Benedicts, was talking yesterday. She is doing some crater counting for the surface of Mars to work out how old different parts of the Martian surface are, which is pretty cool. So we know these impacts have been happening throughout the history of our solar system, and we're going to come back to that in a little while. So we're going to go back to the very start of our solar system. I say the very start, probably not quite the start, maybe a little bit after the start, and we're going to think about how planetary bodies form. So we know at the start of our solar system there was a lot of dust flying around, and these little bits of dust started to come together through static forces, little bits of dust sticking together, and over time that builds and builds and builds, and we have much larger planetary bodies. Now, they probably started out as kind of like rubble piles, if you like, and then over time, if they become big enough, we start to see some of that melting, some of that heating in the core of this planetary body. And over time, this could lead to what we know as differentiation, so where we have the heavy elements in the core of the planet and the lighter elements on the crust of the planet or the planetary body. And then we end up with things like we see on Earth and in the terrestrial planets, where we have a metallic core and we have more of a silicate-rich crust on the outside. Now, I'm not going to go all the way over to here. I'm actually going to focus on these guys, these little rubble piles, which, for the purposes of what I'm going to talk about today, a lot of asteroids can be considered as rubble piles. So why am I talking about these rubble piles? Well, meteorites such as Murchison, a lot of the carbonaceous chondrites that we have, would have originated from these rubble-like bodies. Maybe they've seen some heating, some melting, some aqueous alteration, but they probably all started like this. So the phrase that I would like to use is fairy floss asteroids, and that's actually a phrase that other manager, I suppose, Phil Bland, who we heard talk earlier today, he actually came up with this phrase. Now, the reason behind that is that when I mentioned about these planetary bodies are basically just little bits of dust all coming together, sticking together through static forces. So how did we get from that point, like fairy floss, very fluffy if you like, it's all very glamorous, isn't it? How did we get to this? Now this is the Dingle meteorite that we found as part of the Desert Fireball Network work. So how do we get from a fluffy asteroid to consolidated rock? Because if it was fluffy, it wouldn't make it through our atmosphere. We wouldn't be able to pick it up on the ground. So we've got a process that's happened here, and we're trying to work out what that process is. Now, we could say, okay, well, you know, planetary bodies are forming, they're getting bigger and bigger, gravity is going to be at play. Maybe gravity pulled all those little bits of dust together, condensed them down, squashed them down, until we had consolidated rock. What about the heating that we've been hearing about? The radionuclides, as they're decaying, releasing heat. Maybe the heat has compacted them down as well, and that's absolutely something we need to consider. But if we go back to what I was talking about earlier, impacts in space, we know they've been happening for a really long time. So what effect would that have on our planetary bodies? Now, again, if we consider the start of our solar system, there's a lot of material. And so the likelihood that some of that material is going to knock into one another is quite high. And we've already seen evidence of two asteroids or planetary bodies coming together and just kind of staying stuck that way. So we're going to focus on the effect that impacts would have. Now, the way I'm a geologist and the way that I do a lot of my analyses is using a pretty fun and cool technique. So if we think about what we would see if a body had been compacted, we need to know what the grains are doing in our rock. Now, this is a pretty high resolution image. I think side to side, this image is something like 50 micrometers. So we're looking really, really, really closely. So I'm looking at really tiny things to try and answer really large scale questions. So the technique that I use to understand these tiny, tiny grains within our meteorites is called electron backscattered diffraction. Now, all that means is I get beautiful maps like this. I love my job when I get to look at pretty images like this all day. But what these colours are actually telling us is the orientation of each of those grains. Now, I'll come back to that in a little while. So if we've had compaction on a planetary body, what do we expect to see? Now, as I was writing this talk, I was very hungry, and I kept thinking about what analogies can I come up with here. And I basically finished up with meatballs and rice, because I was hungry, of course. So within these rocks, these carbonaceous chondrites, we know that we have chondrules, which we've heard a little bit about, and we have matrix grains, which are kind of the sea around the chondrules. Now, if we imagine that the chondrules are the meatballs and the matrix is the rice, we might have a situation over here in our bowl. If suddenly we start to squish our rice and meatball situation down, so if I'm squishing from the top down, and maybe the bottom as well, so squashing it like this, we might end up with our rice grains starting to flatten against the edge of our meatball. And we get that on both sides. But our meatball in the middle is probably just fine. It's still nice and spherical because the rice has been moving around it to accommodate that reduction in space. Now, if we continue to squish our meatball and rice situation, we might end up with some elongation of our meatballs. And there's obviously more meatballs happening in here. And then our matrix grains are kind of squishing in between, but still flattening against the edges of that meatball. Now we're gonna stop talking about food because it's gonna make me even more hungry. So this happens in meteorites. So we have chondrules in some meteorites. We have chondrules that are actually elongate, and that would be to do with the fact that they have been compressed by some force. And our matrix grains also sit, elongate, nice and happy in between our chondrules as well. So I mentioned that we look at the orientation of each of our grains. Now, we can approximate a grain as like a rectangular prism, if you like, or alternatively, sausage dogs. Now, the reason that I'm saying this is because I think about this a lot, and I like to bring things like sausage dogs into the equation. So when I say we're thinking about the orientation of those grains, we can approximate our grain, or our dog, with 3 axes. So if we put one axis through the length of the dog, this poor dog, we have one through the length of this dog, we have one through the side of the dog, and top to bottom. Now, I'm going to use those axes to tell me what direction my dog is looking in. And the reason my dog might be looking in a certain direction is to do with a process. So if, for example, we bring out food, and they're food-motivated dogs, which I feel like all of them are, they might all look at you. So they're all looking in the exact same direction because they're expecting their dinner. And that's that process. You've brought out food, they're looking at you because of a process. Now, all of those axes are in exactly the same orientation. We can see that using the technique that I do, with those pretty maps with all the different colours. And if we have no alignment, it's chaos, there's toys, there's food, there's people everywhere, dogs might be running in all different directions, and we have no alignment. So all of those axes are in different orientations. Again, that's something I can see with the technique that I do. So if we think about alignments in meteorites, so this meteorite is the Allende meteorite, which is also 50 years old this year, that we've heard a little bit about. And I've spent a lot of time with this meteorite, so we're pretty good friends, I think. This particular map is, again, showing color coordinated to show you the orientation of those grains. And it kind of looks like a speckled mess. So what we've got here, so this is a chondrule, this is a chondrule, this is a chondrule, this is a chondrule. This guy in the middle is something we call a calcium-aluminium inclusion. This is a chondrule. And we're basically ignoring all of those big things, and we're concentrating on what the matrix grains are doing. So if we remember those matrix grains, if they've been squished, they're probably aligned and flattened against the larger components, or the meatballs. And what I found by looking at this map, so I should mention there's about 600,000 matrix grains in this map. What I found in each of these areas that I've just highlighted is that they do flatten against those larger components, those meatballs, those chondrules, if you like, which is something we'd expect if there have been compaction happening. Now, I also want to note that when we talked about the elongate chondrules, people have definitely seen that in this meteorite. When we look at the calcium-aluminium inclusions, we also see that there's been an elongation there. So if we know we've had this flattening of matrix grains, we can start to think about what direction was this squashed in. And I think it's probably like this. Now, the matrix grains are flattened around the edge here, they're flattened here, they're flattened here, flattened here, and they're all flattened in this direction. So that says to me that we have a compression like this. So that's pretty cool. So now if we move on to thinking about what would happen if we, in the process of compacting this rock. So Phil Bland did some modelling with his team about what would happen if you have compaction of a rock that is made of meatballs and rice. So we have these little guys here that are chondrules, and we also have the matrix in between. Now what he found is when we go from these fluffy asteroid-type bodies, and we then put a shockwave through them, a very slow shockwave, we end up with heating, and we end up with pressure, obviously, but it's not uniform. We don't see that everywhere. So what he found was within these chondrules, they actually typically don't experience much higher temperatures. But in the matrix grains, we do have much higher temperatures there because the void spaces between them are collapsing. Now, we can test that by looking at deformation, crystal bending, so bending of those grains. If you imagine you squash a marshmallow, it's going to bend. We can see that in our crystals as well. So what we found was in keeping with that modelling that Phil did. So this is the side of a chondrule, so side of one of those meatballs. And what we found is that in the centre, we don't see much in the form of crystal bending. But as you approach the edge, we do get a little bit more crystal bending. Now, this is probably not the best example to show you, but it's the only one I had on my computer, so I apologise. But we see this, and this is in keeping with what his models were for compaction of that fluffy body. And then if we look at the matrix grains, those little grains, we see much larger amounts of crystal bending. So we said that only happens at the end with those chondrules, but it happens throughout the grain in our matrix grains, and we expect that. We expect there to be heating in the matrix, more pressure in the matrix than in chondrules. So this is in keeping with what he was saying as well. So what does this actually mean? What am I trying to say here? There is evidence of compaction via impact on these early bodies. I'm not saying that is the only reason that these bodies were compacted, but it's certainly a driver. And we know that impacts were happening throughout the history of our solar system. And so modelling what that might look like has kind of led us to here. Murchison probably experienced this on its parent's body, but as we've heard, there's been a lot of changes that have happened to that meteorite since this probably happened. So we might not actually be able to see the evidence of that process. So as I said before, it's probably been overprinted by processes such as melting and aqueous alteration, but that's actually something else that I can test, and that's what I'm trying to do right now as I'm continuing with my research. So thank you, and I'll try and answer any questions you have.
Do we have any questions?
It's okay.
I certainly do. Because I was wondering, we've seen a lot of slides of meteorites across the weekend, and we haven't seen a lot of fabrics. I mean, I think it was that Mike showed, or was it Phil showed one with what was an obvious crystallographic like fabric.
Yeah.
But that's an anomaly with what we've seen this weekend. So there's not a lot of really obvious deformation. You're seeing it's quite subtle.
It's very, very subtle. Very, very subtle. I mean, the big map that I showed you, until recently, I could only look at tiny chunks of it, just because the software wouldn't let me do the whole thing. It panicked and crashed every time. But we do see a fabric across the whole section, but it's so weak and so subtle that perhaps people would say that there isn't a fabric there at all. But I respectfully disagree with that.
Right. So can you calculate the sort of momentum involved and the forces involved with the impact, the typical impacts that you're going to see in these belts? Is there any way of modelling what's likely in a belt of sort of semi-chaotic material?
Probably someone who has a lot more experience in modelling than I do, which is anything, because I have no experience with modelling. But that's definitely something that we need to look into in the future. This kind of, the modelling that Phil did is kind of wouldn't say a first pass, maybe a second pass approximation of what's going on. But of course, it's very simplified in terms of all the different components and all the different impacts that can be happening and the nature of those impacts. So there's a lot of scope to vary those.
Okay, so we're really just starting to learn about these things, plus muddy things.
Yeah, muddy things.
Martin.
In the slide where you showed the little compaction of the matrix,
Yeah.
some of the chondrules were quite elongated in other directions.
Yeah.
Do we actually know that chondrules are always spherical? Some of them look quite ragged.
Yeah, I absolutely agree. Yeah. Yeah, it's absolutely been reported that chondrules, especially in that meteorite, are more elongate, and especially the CAIs as well, the calcium aluminium inclusions, are also very elongate. I'm trying to understand why there is a difference between the matrix and the chondrules and the CAIs, because that's something I see, but that's something I'm doing right now. And I actually went to Phil last week and said, I don't understand, and he's like, so that's something we're questioning at the moment too.
Right down the back there.
I'm just wondering about the pressures. We're talking about gravitational pulls and all the rest of it. Are we talking about large pressures, or are we talking about low pressures and small shock waves over a very, very long time to consolidate these bits and pieces together?
Yeah, so we're definitely talking, sorry, take it off.
That's it.
Okay. Yeah, so we're definitely talking about these pretty slow, pretty small impacts. Apologies, I should have said that. We're kind of thinking about, in this planetary body that we've got, because it's quite small, we're not expecting gravity to play a huge role. Of course, we could be wrong, but in this work, we're anticipating that gravity is probably not sufficient to compact that body down. So we're thinking about small impacts, very, very little impacts over the course of time that have slowly but surely compacted this body down.
And
so is this only happening while it's travelling, or is the compaction happening before it travels?
Do you mean before it's coming down as a meteorite? Okay, so this is happening when it's on its parent body. So this is before the aqueous alteration that we've heard a lot about this weekend. This is before the fragmentation for it to come to Earth and land as a meteorite. So yeah, really, really early on. Yeah.
yes.
Is there any thought about how big the parent body was that seeded that caused the Murchison meteorite?
I'm not sure about the Murchison meteorite. I'm sorry about that. I can check on that for you though.
I think that's one of the big unknowns. Speculated to be potentially many kilometres across, but we don't know. Okay, thank you, Ellie, in appreciation, token of our appreciation. Sorry, Lucy.
That's
Ellie.
okay.
Lucy, thank you very much for coming over and sharing your knowledge with us.
Pleasure. Thank you.